Okay. So nearest neighbors, remember we introduced them in part 1 of this course when we just looked at basic tools. And then we went on and derived essentially Poisson windows, Watson-O'Donnell style estimators. And there was actually a really cool question that came up on Piazza. I don't know whether you saw it, but this question went along the lines of, well, can we have different weights for the neighbors within the neighborhood, right? And effectively, that is the Watson-O'Donnell classifier, right? That's basically a device that picks different weights within a neighborhood. And I just want us to go through that and formalize it a little bit, just to give you some more intuition why on earth nearest neighbors is actually not a totally crazy thing to do. So we all remember nearest neighbors. It's basically, take the nearest neighbor, give it that label. Now, let's look at Watson-O'Donnell. So remember that for regression or classification, what we had is basically we had the sum over local weights. These guys here. These are local weights. And we weigh the yj's accordingly. And that's it. Now for a nearest neighbor estimator, we basically do the same thing, except that our weights are chosen in a slightly funny way. Sorry. These weights, because they are basically 0 or 1, depending, or 0 or 1 over k, depending on whether they are the k nearest neighbors or not. Right? So in other words, nearest neighbors is just an extremely ham-fisted way of doing Watson-O'Donnell. It's not the most sophisticated way of approaching it. However, it's much faster because you only need to perform a nearest neighbor query. You can sometimes perform approximate nearest neighbor queries, and that's why people prefer it sometimes. Both of those algorithms are fairly solid baselines, and if you come up with a new algorithm, I strongly urge you to compare it to things like nearest neighbors. Because it's way too easy to come up with a new algorithm and be super excited about it just to find out that it cannot even beat nearest neighbors. And yes, that has happened to me as well. So, happens to anyone. Well, maybe not to you, but I hope it doesn't happen to you, because otherwise you'll be very frustrated. So, these were the nearest neighbors. Yeah, it shouldn't be 4, it should be 7. Anyway, now here's what happens. If you think about it, the one nearest neighbor, it converges to the perfect solution if we have a clear separation, right? That's the case on the left. This one here is all fine. It will converge to twice the minimum error rate for noisy problems. Yes, basically what can happen is that you still get unlucky that the nearest guy, without loss of generality, the nearest guy with probability p will be of one class, and with probability 1 minus p will be of the other class. And so you basically need to count all the cases where things can go wrong. It's basically one case is that you pick the wrong class with probability p, and then the test point has probability with probability 1 minus p is the wrong label. And it can also happen that you pick the correct class with probability, the majority class with, probability 1 minus p, you get this guy. And so this is why you pay a factor of 2. Now, the second case is inevitable. You basically vote with the majority class and you get the wrong guy. Okay, fine. The first case, where you pick the wrong label as my label for that neighborhood, that is the case that you want to avoid. That's the case that you can eliminate, right? So basically, you have one case where you have, a red circle and then a green square as a test. And you have another case where you have a green square as a test and a red circle. Okay. And let's say if this occurs with probability p, and this occurs with probability 1 minus p, And let's, without loss of generality, assume that p is less than 1 minus p. Sorry. Okay. So this is okay. There's nothing we can do about this case here. This case, there's nothing we can do. That one we can avoid, because that basically just happens if I end up with the wrong nearest neighbor. I can actually make that probability that I get the wrong nearest neighbor guy go to 0, simply by picking k nearest neighbors. Right? And then everything's okay. Now, the way how you prove it is you basically just, take a neighborhood, let the size of the neighborhood increase let the size of the neighborhood decrease slowly while getting more and more points within that neighborhood. And that's it. Okay. Now, there are a couple of things that you can do to do a fast lookup. So one way is, for instance, to use what's called KD trees. And if you'd done that about over a decade ago, you might be dean of the Department of Computer Science now. So Andrew Moore, he's the guy who did this. Andrew Moore and Alex Gray. Alex Gray now has a fairly successful startup, and Andrew Moore is dean. So they did something right. Basically, what you do is if you think about if I wanted to perform nearest neighbors on a line, right? Suppose, I have just a line, and I want to perform a query, let's say here, what's going on. So in that case, if I have all those points on the line, how would I perform a fast lookup for scalar variables? Okay. Any ideas? How would you do that? Yes?
Pre-sort it and do a binary search?
Exactly. Pre-sort and binary search. So you run a quick sort, and you perform a binary search. By the way, I hope that everybody here in the room knows what quicksort is, right? If you do not, please check. Now, I just got an interesting surprise yesterday when talking to somebody, and yeah. So basically, sorting and dictionary lookup is very easy. Now, if I have 2 dimensions, I can still do that, right? It's just that the lookup is now a little bit harder. I basically could go and, partition my space, and partition, and you'd be fine. Or maybe you adaptively partition based on the data. And this adaptive partitioning and doing it very cleverly, that's exactly what's in KD trees. And the nice thing is that this is very fast in moderate numbers of dimensions. Moderate dimensions meaning like tens. Not hundreds, not thousands. Now, suppose my data is actually reasonably well behaved, but it lies in this extremely high dimensional space, right? And nobody told me that it lies in this high dimensional space. And maybe it's actually in a manifold in this high dimensional space. So with manifold, think of a sheet of paper that's somewhat warped and twisted up a little bit and scrunched up. It's still, a sheet. So the question is then, can you do something efficient there? And there's a really cool algorithm called cover trees, which is a little bit more powerful than KD trees. And it basically builds a binary search hierarchy to go through this. It's a really nice paper. So if you get some time, read it. It will help you probably accelerate a whole bunch of algorithms that you have. And it really depends a little bit on how nice your data is, how rapidly you can do this. But it's a really, really nice idea. Essentially, what you do is you have a dyadic tree not dyadic, but basically you get a search tree where all the children are within a factor of 2 of the accuracy of the parents. And you can walk down this tree, and by reasonably clever construction, you can make sure that you don't have to trace too many branches at any time. So look at the paper. It's very, very pretty, and there's actually code with it. Okay. Now let's get to the main attraction of today, namely exponential families. So this will conclude the statistics part, and then from next week on we'll do a little bit of systems, and then we'll get back to doing math again. And yes, sorry, statistics requires math, so we need math. Yeah. Okay, exponential families. So let's first go through things that you could do with exponential families. And I'm going to throw the two key equations at you right away. So if you remember nothing else but those two equations from this class of today, you will probably be fine. Who has heard of exponential families before? Okay. Who's heard of maximum entropy before? Okay, good. So then that means actually that most of you who've seen or heard of maximum entropy estimators would have actually worked with exponential families, just that nobody told you that that's what you're doing. Okay. And we may actually prove this in class or maybe do it in the homework. So here's basically what happens. I'm assuming that I want to estimate some density or distribution over x, so p of x, and I parameterize it by theta. So theta are the coefficients by which I parameterize this. And I'm going to write it in a way that initially looks a little bit scary but actually isn't. Namely, it's the exponential of the inner product between, well, some features of x and this parameter. And then all I need to make sure is that this is actually a proper probability distribution, so I need to normalize by g of theta. So this g of theta does nothing else but just make sure that the entire thing integrates out to 1 or sums up to 1. This g is therefore, I can actually derive it. Well, let's actually do this. So let's see what happens if we derive it. So after all, I need to make sure that the sum over x of some coefficient times e to the phi of x dot theta equals 1, right? So therefore, I can actually, remove the c, bring it over here. So I can remove it, and I get 1 over c. And, well then, what I simply do is, I take the log of this, and I get the log here. And I call this thing here simply minus g of theta. And then when you plug this back in here, you get exactly the expression that we had. Okay. Is anybody stuck at this simple derivation? It's really just computing a normalization. The reason why we write this g in this very, very bizarre form, because, after all, I could have just written it like so, right? I could have just picked this, is that this function g is actually going to be nice and convex, and its derivatives will have all sorts of wonderful properties. That is the main reason why we're writing it in a slightly more complicated way, to make our life easier later. Okay, somehow I need to send this away. So the nice thing is that, well, and I'm actually going to derive this for you, that the first derivative of g will give me the expected value of phi of x, and furthermore, the second one is going to give me the variance. Okay. Now, why? If those two things are true, does it hold that g is convex? Okay. Why is the, why does this follow from those two lines? or actually from this line. Because the variance can never be negative, right? That's why. Okay, this sounds pretty cool. Let's actually prove it. At least we'll take the first derivative. The second one may be a little bit painful. As in, it's not painful, it just requires a lot of writing. Okay, so remember we had g of x, or g of theta, to be the log of the sum over x e to the phi of x dot theta. Okay, so d theta of g of theta is, well, first we need to deal with the log, so we get something in the denominator. So we get sum over x e to the phi of x dot theta. Can somebody tell me what this quantity here in the denominator actually can be rewritten as? I can write it as e to the g of theta. Right? Because that's just how I defined this. Right? Now we need to deal with the numerator. So we have the sum over x e to the phi of x dot theta, because it's the exponential. Now I need to take the derivative of the inner term here. And so I get times phi of x. Okay. And now I'm just going to pull the e to the g of theta into the exponential here. So I can rewrite this as sum over x. Oops. Thank you. Man, great. Yay. Nice user interface. Thanks for letting me know. So that's just our exponential again. Phi of x dot theta minus g of theta times phi of x. Right? So I have not done anything terribly deep beyond what you might have learned in the first year analysis class, right? Just simple first year calculus. And all I've done is I've just moved the g of theta in here. Now, this quantity, we already know what it is, right? This quantity is nothing else than p of x parameterized by theta. And so in other words, this is plain simply the definition of the expected value. Okay. Is that step okay?
Would the continuous case be exactly the same?
Yes, the math goes through exactly the same thing. All you do is you replace the sums by integrals. And yes, we are assuming that we can just differentiate through the integrals. And yeah, we are basically ignoring all the things that a good mathematician would actually be really worried about. So you need to make sure that everything is nicely integrable and so on. Yes. But the point is, okay, so basically we are not going to worry much about measure theoretical issues in this class, right? If you're a mathematician, you might actually be quite upset about this, but yeah, okay, basically This is, yeah, we can do the cleanup later, essentially. Yes?
Another question. Cumulants.
Pardon?
What are cumulants?
Okay, so cumulants are basically higher order moments. Well, they're not quite the same thing, so one thing is centered and the other one isn't. But so to give you an idea of what's different, so in one case, you have the expected value of x squared, and in the other case, you have the variance. So the variance would be a cumulant. That's essentially the main difference. So if you were to compute the second derivative here, what you would simply end up getting is then the variance, right? And it's basically just that type of derivation with about twice as many lines. And I urge you to do this once for your own benefit. You probably will not want to do it twice or 3 times, and I've probably done it more times than I wanted to. So, yeah. But basically, this is an extremely useful property to exploit. Okay, so is everybody at least slightly comfortable with the idea of an exponential family? Okay, so don't worry. I mean, we're going to look at lots and lots and lots and lots of special cases. We'll look at lots of examples, but this is really the basic equation. If you just remember that slide, you can pretty much rederive the rest of this lecture from that slide. And it's not rocket science. But sometimes when it's written out in statistics papers, it's written out with, I think, unhelpful notation. And then, the first time you read that, okay, we use a Dirichlet distribution as a conjugate to a multinomial, you will, just be slightly intimidated, right? But it's actually something very, very simple that's going on behind the scenes, and I want to show you that it's simple. Okay, so let's look at some examples. And again, I strongly urge you to go to Wikipedia, search for exponential families, and there's a very long laundry list of different distributions, conjugates, properties, and all that. And most of them have their own Wikipedia page just to analyze them, because the reason why they are so popular is actually a very simple and practical one. Namely, they are very easy to analyze. So that's why a lot of things work out in closed form, and you don't need to use numerical mathematics to deal with them. And that's why they became extremely popular. But of course, they also have useful theoretical properties, and people prove stuff about them. But the fact that a lot of things can be done analytically is definitely a major attraction. Okay. So you may have heard of a Gaussian. Yes, of course, we did. A Poisson distribution, Dirichlet, beta, gamma, Wishart, binomial, and so on. And they actually all only really differ in the choice of this thing here. This is where they largely differ. So by picking a different phi of x, I get a different distribution. And the good thing is the same math, all the same properties hold once and for all. So you prove all those expected value properties and so on once. Then you just apply them to all those distributions. So let's actually look at them. Let's pick the simplest thing first, namely a binomial distribution. And by now it might become a little bit clearer why in the beginning we worked out this completely wacky parameterization for a binomial distribution. So let's assume that we have features phi of x being x, and that the domain is 1 or minus 1. So maybe 1 being apples, minus 1 being oranges. Okay, so what's this thing here? Okay, whatever. So in this case, the normalization g of theta is just the log of, well, e to the, theta times phi of minus 1, and that's just minus 1, plus e to the phi of 1 times theta. And since they're scalar, inner products just become products, right? And that's just log of e to the minus theta plus e to the theta, and that's just log 2 cos theta. Right? So this is easy to plot. And so now if I want to work out the probability p of x parameterized by theta, well, that just works out to be e to the x times theta, because phi of x is x. It's exactly what we had here. Let's go in there. And the log 2 cos theta go in here. And if you expand and rewrite it, you get this. And this was exactly the logistic function that we had before. So some of you may have seen the logistic function. And it's this very, very simple beast here, right? So if I were to plot it, I'd get something that looks like so. And yeah, here's 0 and here's 1. Here's 0. And it'll be 1/2 in here. And yeah, here's the plot. Much prettier than what I could have done. So there's a slight difference between what I plotted here and on the previous slide. Can somebody spot the difference? Yes?
It's e to the negative x theta here is negative 2x theta.
Correct. So I just did that for notational convenience. You could have also achieved the same effect by not having phi of x being x, but just 1/2 x. That would have also done the trick. So this is why sometimes you get a 2, sometimes you don't, just depending on how to make your life a little bit easier. But just keep that in mind when you do the analysis. Sometimes people also use phi of x being x and x being the set of 0 and 1. Then you get a slight shift. And so all those things are, of course, the same math. It's just that you perform different affine transforms. So you need to be a little bit careful how people write it out. There's no mathematical difference really in it. It's just that sometimes it looks prettier one way or another. Okay. Now here's another one. The normal distribution, and this is straight out of Wikipedia. Well, different pictures of normal distributions. I guess everybody would have seen a Gaussian before in their life. Right? Yeah. And so, of course, if I shift the mean, well, the bump moves. Right? That's basically here. And if I change the variance, well, this gets wider or narrow. Okay. Quick sanity check. Which of those distributions has higher variance? Okay. Let me just. Okay. So, does the blue curve or the yellow curve have higher variance? Who opts for the blue curve? Who opts for the yellow curve? Okay, I think the majority has it right. Basically, more spread out means that the values are all over the place, and that's about it. Okay, next sanity check. Who thinks the green curve has higher variance than the red one? Okay, who thinks the red one has higher variance? Everybody goes up. Okay, so that is true for the variance. For the cumulant, it may not necessarily be true. Basically, the expected value of x squared may actually be higher for the green one. But that's not the variance. So we may actually get to that in a moment. So, well done. Let's just look at the Poisson, and then we can go through a little bit of the algebra and work it out in detail. So the Poisson distribution is something that you often use if you want to deal with point events. So point events, for instance, one way to derive it is, suppose I want to count how many snowflakes fall in, usually people talk about raindrops, but this is a class in winter. So suppose we have, a nice, square inch or square foot area, and I want to estimate how many snowflakes fall within a given amount of time. And since I can assume that, well, the overall intensity of snowfall or of rain is the same, the chances that a snowflake falls at any given time is a random event. And so I can actually model this using a Poisson distribution. Another case where this happens is, for instance, if I want to model how people write news articles about things on the internet. So, for instance, if you were to look at the distribution of blog posts about Left Shark, you would see that, after the Super Bowl, you would have this nice spike, and then you will actually see people feeding off each other, and you get the feeding frenzy of Left Shark articles. And at some point, this will hopefully die out. One of the earlier examples is when so in the Prussian army, they were pretty good at essentially record keeping. So, Prussians were known for doing everything by the book, so to say. And so one of the things that they did is they kept record of how many soldiers were killed by being kicked in the head by a horse. Okay, so it's a very rare event, and it's essentially random. Basically, the horse has a bad day, and maybe the soldier is drunk, or whatever, but it's essentially random. And it turned out that if you look at that distribution over the years, it would follow exactly that type of Poisson distribution. Okay, so let's actually study that distribution in a little bit more detail. What we have here is lambda to the x. So x is the number of counts. So x is an integer, can be a 0. E to the minus lambda, that's our normalization, and x factorial. So what you can see is that depending on how large a lambda you pick, and lambda actually turns out to be the expected rate anyway, you will get something that will peak somewhere, and then it just decays. And the magnitude of the peak, the position of the peak will depend very much on lambda. So for large lambda, of course, the peak is further out to the right. Okay, so it actually turns out, and we probably don't have time to go through this algebraically, but you can easily work it out yourself, if you have a binary random variable and you toss it many times, then if the expected value of that random variable, let's say comes up heads or tails with probability 1/2. Then if I toss it many, many, many times, we already saw, with the central limit theorem, this will converge to a normal distribution. Right, we saw that. Now, I can also make a different limit analysis. The other limit analysis would be to say, let's actually assume that the expected value of the coin tosses is 10. Okay, so we pick this guy, 10. However, what I'm going to do is I'm going to take more and more coin tosses, and where maybe initially I might have had 10 coins which came up heads with probability 1 each, at some point I will have maybe 10,000 coins where each of them comes up with probability heads of being 1 over 1,000, and you make that limit transition. So you keep the expected value constant by making the individual probabilities smaller. If you make that limit behavior, you of course can end up with cases where you get way more than 10 coins coming up heads, and that distribution limit is actually the Poisson distribution. So this is something that sometimes when you want to model basically distributions over events where within each time segment things have an infinitesimally small chance, but you have a lot of those segments, then the Poisson model may actually be pretty good. Can somebody tell me when the Poisson model may not be appropriate in such cases? Okay. So one of those cases is, for instance, epidemics. So take something like Ebola. And the problem is basically once you've had it, you're very unlikely to get it again because you either die or you become immune. So while maybe initially, given constant exposure, you might actually have a Poisson distributed random variable and possibly some feedback effects, at some point you will not be likely to get that same disease again. So the Poisson approximation there is only valid in the case where the outbreak is extremely rare. So cancer, for instance, would do that because you can get it again if you've had it before. Yes? You were asking a question? Okay. Good. So here's something called the beta distribution. Yes?
In that case, does that matter for independence? That you can do it again, otherwise the
Yes.
population is...
So what you can actually do is you can use something called a Hawkes process and use what's called hazard regression. So there's a lot of very nice extensions of essentially point process theory that you can bring to bear on this. This is quite a bit beyond 10701. If you want to know, talk to me later. We're working on a few fun things in this context. Okay. Beta distribution, this is actually, as we'll find out later, a conjugate to the binomial. And it's also useful if you want to model distributions of that form. You can do it actually very easily with just a few parameters. Okay, this is what's called a Dirichlet distribution. It's essentially the generalization of that. And one way to sometimes view it is that people think of this as a distribution over distributions. Okay, so let's let that sink in, because it's the first time you encounter that. It sounds weird, but it's actually perfectly natural. So in this case, what we have is a probability simplex, right? It's basically over 3 possible outcomes. Let's say this is outcome 1, outcome 2, outcome 3. That's just a triangle, equilateral triangle. And now, what I can do is I can model any distribution of outcomes over those 3 events by just any given point within this triangle. Let's say here or there or there. Right? Why is that the case? Because I really only have 2 degrees of freedom, because all 3 probabilities have to sum up to 1. So a plane is perfectly sufficient to represent that. Right? So you may have done similar things in chemistry when you had stoichiometric mixtures, and where basically the mixture between different states, or for instance for state transitions, would always have to sum up to 1. So if you have a eutectic state or other state transitions in, solid, liquid, matter, whatever, you can actually get stuff like this. Now, what I can do is I can simply have a distribution over those mixtures, in this case, 3 different outcomes. And so I can draw from that, and I get, some now mixture of 3 possible outcomes. This is actually an extremely useful thing to do if I want to model a distribution over 3 outcomes, and I don't quite know what the individual probabilities are. Because then I could, for instance, say, well, I have absolutely no idea, so I just make that prior distribution entirely flat. Or I can say, well, I'm fairly sure it's exactly 1/3, 1/3, 1/3, and I make it really spiky here. Right? So I can do stuff like this. And that's exactly what the Dirichlet distribution lets me do. It basically lets me specify a mode where I think things are more likely to occur, and also basically the concentration of that mode. It will not let me design something bimodal, but at least if I have if I have some good idea of where I would expect things to occur and how much concentrated, that's what you can get. Okay. Yes?
Do these distributions have to belong to the exponential family?
So the Dirichlet distribution happens to be of the exponential family itself.
So the individual...
So there's actually something really cool going on. So both the distribution that I'm modeling, namely this in that case discrete distribution over 3 events, and the Dirichlet distribution, which I'm going to use as its prior, they are both in the exponential family. More generally, what will hold is that for any distribution in the exponential family, there exists a conjugate distribution that is also in the exponential family. Of course, you could iterate that ad infinitum, but at some point the integrals will just become so unpleasant that you want to stop. So the reason why people don't overdo it is just because they don't like solving integrals. So now let's see whether we can actually do inference in this model. So let's look at the negative log likelihood, right? That's after all what you might want to do in a maximum likelihood model. And that's just if I observe some xi's. And I want to, simply compute minus log of p of x given the data. And, well, we all recall what p of xi was given at. So P of xi given theta was what's going on here? Sorry. Exp of phi of x dot theta minus g of theta. Okay. And so, of course, if I take the log of this stuff, I get exactly this term here. So the negative logarithm, right? So I get g of theta minus that inner product. Okay. So now, all we have to do is just take derivatives, right? Because for maximum likelihood, what I want to make sure is that d theta of the log of p of x parameterized by theta vanishes, right? This is, after all, the first order optimality condition, right? So making sure that derivative vanishes will get me either a local maximum or local minimum. However, since we have a convex function, I don't know whether that was already covered in the recitations. If not, it'll be probably either this week or, very worst case, next week. It actually means that if you have a convex function, you can only have one global minimum, as in global minimum value. There can be many minimizers, but only one global minimum value if it's attained. And so therefore, setting the derivative to vanish means that I will actually be at the minimum. And g, of course, as we saw before, is a convex function because its second derivative is all positive semi-definite. Oh, perfect. The chocolates have arrived. Many thanks. Awesome. So this is for the homework for afterwards. So, okay. And, well, so basically all I have to do is just set it to 0. Now here's the really cool thing of why I went on and on and on about the derivative of g. Yes?
Why are we multiplying by m instead of n?
Because it's a typo.
Okay.
Yes. Thank you. This should be n. Thank you. And there as well. Yes. And now the n works. This is what happens if you do cut and paste from previous slides, and or basically from Emacs, and yeah. Okay. So all I did here is I had the sum over n of the g of thetas, and I just pulled the n out, right? So this thing here ended up there. And then I just multiplied and divided by n for the second term, right? This guy here, this one here, and there. Okay, so now what I basically get is that the mean of my distribution has to match the empirical average. Well, we had that before, right? When we estimated, just a discrete distribution over a couple of outcomes, what we did is we, for instance, counted number of emails being spam divided by total number of emails. And let's say that was maybe 0.7. And then we just said, okay, now let's actually set the distribution to be 0.7 for spam and then 0.3 for ham, right? And this is just in a very glorified way doing the very same thing. You've probably done this before also in the context of estimating a Gaussian, right? So you would go and, compute the mean, the empirical mean, compute the empirical variance, and then just plug that straight into your Gaussian. And if you do that, you get, well, an estimate for a normal distribution. So all we're doing here is just formalizing this in general, because you can do that not just for Gaussians or for discrete distributions, but also for Poissons, beta, gammas, Dirichlets, anything you want. And it's the same equation over and over. So rather than proving this for each of those distributions, I prove it once in general, and you can then just apply it. just being lazy. So actually, let's maybe, well, let's see. Does somebody want me to work that through for the Poisson? Nobody wants me to. Basically, well, yep. Basically, does somebody want me to work this through for the Poisson distribution in detail? Okay, then maybe we'll defer it until we have the conjugates. I need more hands. So, if you think about it, this is all very nice, but sometimes those estimates can be quite weak. Because, I mean, as we saw when we toss the coin or roll a dice, if I only roll it maybe 10 times, my estimates will be highly unreliable. But the good thing is that quite often we actually have some idea of what we should be expecting in terms of the data, right? So when, I play, with you and you procure some dice, I'm going to assume that you're an honest person. On the other hand, if I go somewhere to maybe some very shady red light district and go to some, gambling saloon, I will not assume that the people who I'm playing with are nice. I will assume that maybe their coin is slightly biased in their favor. And I will stand to be convinced otherwise. Well, I might just not go there, but if I went there, I would probably assume they want to cheat me. And so one way of doing this is by essentially adding fake data to the true observations. The reason for using fake data is because this way my prior will behave exactly in the same way as if I just had observed extra data. So if I wrote some code for maximum likelihood, I can just modify this code by adding some extra fake data, and I'm then performing, therefore, a maximum posteriori estimate. So I'm basically applying Bayes' rule by just faking it. And this is extremely powerful. So let's actually see what happens. And so sometimes people make conjugate priors this very fancy magical concept, and it's actually really, really simple. So here's basically what I'm doing. I'm saying, well, P of theta should behave like, fake data given, the parameter. So it just should behave just like a likelihood. But the good thing is, of course, that in this case, P of theta given x, by Bayes' rule, well, that's just proportional to P of x given theta times P of x fake given theta. And since I did not make any assumptions about the order in which fake and real data is observed, all I'm doing is I'm just throwing fake and real data into one bin, and so I get this as a form for my posterior. So now,
where does this fake data come from?
it comes from you. So the fake data comes from whoever sets up the experiment. So, for instance, suppose that, so let's say you're a very diligent student and you always bring your homework and you always submit it on time. And one day you come in and you say, I don't know, the car broke down and fine, okay. So my assumption then will be, so I have one real data point and I have fake data by, just knowing that you look like a very honest and reliable person and, you've actually been good before. So then my inference that you lied to me will be, that probability will be very small because the fake data will completely prevail this one additional observation of you being late. On the other hand, if there's some very shady character right over there who, well, never submits his homework and maybe does other things, right, then, well, maybe you will give him less the benefit of doubt.
So is it completely arbitrary?
So, yes, fake data is, so conjugate priors are entirely arbitrary. However, what can be proven is that in the large sample size limit, because, the point is you once set up your prior, and then you start measuring. It's not like you start observing and then you say, well, given those observations, that's what my prior should be. That's not how it goes. You need to place your bet before you actually gamble. So as you observe more and more data, you will actually see that then eventually the real data, the truth, will prevail over the prior. So that's the point where, yes, the prior is arbitrary, but you should do your very best to be a good engineer and come up with a really good estimate of what reality should look like. So this is basically where your skill as a statistical modeler is really, really important. So try to be as reasonable, as sensible as possible. Okay, so let's actually see what happens for Laplace smoothing, right? So remember what we had is, just so if we before that try to match, 1 over n sum over I going from 1 to n phi of xi. So this is what we had in maximum likelihood. Now we basically have n real data points plus m fake ones. And so I need to normalize by n plus m, this term here. And then I have m over n plus m, so m is my fake count, of the fake mean. Okay, let's actually put that a little bit into context, because we saw that before as Laplace smoothing for discrete distributions. Okay. So let's say we have phi of x. It's just Ex, and X maybe being English, German, French, Italian. Okay, so maybe I have a distribution over those 4 possible outcomes. And now what we can do is we can have stuff like M being maybe 10. So this is like I have a assumption that I have the equivalent of 10 fake observations, 10 fake cases of people who came in before, and then maybe English is 1/2, and then maybe we have 1/6, 1/6, and 1/6. Okay. So this would be now my mu. As a mu0. And so, of course, what I get is that m times mu0 is going to give me 5. And then, here we have 5/3, 5/3, 5/3. The key point is my fake counts don't even have to be integers here. Then I'm maybe going to go and observe the following things. I'm going to observe maybe English, Italian, in other words, no Germans, 1 Italian, 1 French. So my sum over I going from 1 to n phi of xi is going to be what? What's the first entry? How many English do I have in this set of 6 observations? 4, right? There's no German to be found. 1 French, 1 Italian. Okay. So I basically have a total of 6 observations. I had a smoothing prior of 10. So now what I get is that my probability estimate would be 1 over 10 plus 6 times. Now here we have 4 plus 5. We have 5/3. We have, in this case, 8/3, and we have 8/3. Okay. So this would now be my probability estimate that I get by using a prior, a concentration parameter, and some real data. Now, this is essentially just a fancy version of Laplace smoothing that you would have done before if you worked on language, where you basically take the true counts and you add 1 to all the true counts. Except that we took the liberty of adding, well, something that's not an integer. Yes?
Would you also need to divide n times mu0 that vector by 16?
That's what I did. Right? So we just added it up and then divided.
Oh, I see. Factored out.
Right. So this guy, they both contribute likewise there. So that's, all I did is I just made my life a little bit easier by writing the upfront factor of 1 over n plus m and then having both sums on the inside. Okay. Now we can actually do the same thing, for instance, for a Gaussian. And for a Gaussian, interesting things happen. So let's do something as follows. Okay. So in a Gaussian case, we have phi of x being, let's say, x and then 1/2 x squared. And the 1/2 is just there to, yes?
So what's a good choice for m, typically, given the fact that we don't quite know
Okay.
how much?
Yes. So what's a good choice for an exponential family? Well, first of all, the domain needs to match what you're dealing with. So in other words, if I have just a discrete set of outcomes, something like a Gaussian or a Poisson distribution is not going to be so great because the domains don't even match up. And secondly, you probably also want to make sure that, for instance, things like cardinalities match up. So if I have counts, Poisson is kind of the go-to distribution. If I have real value scalars, or maybe just d-dimensional scalars, a Gaussian may be a good choice. Now, this sounds extremely restricted, right? Because why on earth should this be good? And as a matter of fact, it doesn't fit most of the data terribly well. The way how you can then address this is by imposing a mixture model on top of it, where you would say, well, my data that maybe is not really Gaussian, but it is combined. But there are clumps in the data that behave like a normal distribution with maybe different means and different variances, and you then are going to approximate the entire set of observations by those clumps. So that is effectively how you can work around the fact that not everything is a terribly good match. And so, for instance, mixture of Gaussian models are extremely popular as density estimators. Okay, there was one more question.
So I think the question was how much fake data. How do you know how much fake data to include?
Okay, so preferably you don't want to include more fake data than real data. That's the first thing. Secondly, it really depends on how richly parameterized your model is. If you have 10 parameters, then it may not be a bad idea to have the equivalent of maybe between 10 and 100 fake instances. So basically, number of parameters, equivalent data is probably a good idea between 1 and 10. That's not a bad choice. So those of you who might have invoked EM clustering at some point and found some variances to diverge, that can be very easily fixed with conjugate priors. Let's actually look a little bit at what happens. So here's exactly the Gaussian case. That's what I promised you just in a moment ago. So let's take our sufficient statistics to be x and x squared. And, well, we know that the mean and the variance are given by, mean is very simply given by the expected value of x, and the variance is just the expected value of x squared minus the expected value of x squared, right? So that's, everybody knows that, I think. Do I need to derive that for anybody? I don't think so, right? And we all know how the maximum likelihood estimate is obtained. So I will go and pick mu to be just the empirical average and sigma squared to be, for instance, this quantity here. Now, what I end up doing for a maximum posterior estimate, and you can actually derive all that with a student t or a Gauss-Wishart distribution, and the math becomes extremely unpleasant. In the end, you end up with a very, very simple equation, namely this one here. So that's why I'm just showing you an extreme shortcut, because otherwise you will probably spend about half a page of math on getting this result and then be very surprised that you get a very simple result. Is basically the following. So what I do is, as before, okay, let's work it out in detail. Document camera. Okay, let's drop the 1/2 here. Okay. So my assumption is that I have some mu0 or some mu, which is given by maybe 0 mean and unit variance, right? So the expected value of x is 0. The expected value of x squared minus the expected value of x squared is 1. And I'm going to assume that I have some concentration parameter. Okay, on this slide it's called n0. Not specifying it any specifically. Okay. So then, in order to get mu hat, I need to compute 1 over n plus n0 of the sum over I going from 1 to n xi plus n0 times 0, right? Which gives me exactly the very first line here. Because, well, it's on the right display. Gives me this. Because, of course, 0 times something goes away, so I can just remove that entirely. So, for instance, if I have a normal distribution, assuming 0 mean is sensible. On the other hand, if, for instance, you're going to try and estimate, let's say, the voltage coming out of those sockets, 0 mean is a pretty stupid idea. And you would probably want to pick something like 110 or 115. And since we never really know exactly what the voltage is, okay, well, let's pick 110. And I'm just not amazingly confident, so I'm maybe confident to the extent of having made maybe 3 measurements before. So, in that case, I would just have, plus 3 times maybe 110. Okay. That's if I was to run around with a voltmeter. Now, for the variance, I get a similar thing. So I get sigma hat. I get 1 over, we basically need to estimate the value of x squared, right? So we have, that's what gave us mu. We also need to estimate the value of x squared. And this is where things get a little bit more complicated. 1 over n plus n0. Here is sum over I going from 1 to n xi squared, plus now I need to get the expected value of x squared here, which is 1. So I have n0 over n plus n0 times 1. And that is actually the estimate of x squared. And what I then do is I simply use the fact that sigma squared is, expected value of x squared minus expected value of x squared, and plug this in. And so, of course, I will need to use mu hat, my estimate, because I'm estimating both terms. Okay. Now, what would happen with the voltage in the socket? Can I add times 1 in here? Let's assume I'm assuming in the same way that I have a variance of 1 volt, which is ridiculously low, but okay, fine. Does it make sense to add 1 here? Is that correct? No, because, of course, the expected value of x squared, right, is sigma squared plus the expected value of x squared, right? It's those 3 terms down here. So I would have to rewrite this as 110 squared plus 1. So in other words, this would be 12,101. So what we're seeing here is already something that's quite interesting, namely that the values of x and x squared, the expectations, and also the observations here, cannot be from an arbitrary set. Just a moment. So basically, what happens is that they are from what's called a convex cone. And in this case, it's a semi-definite cone. Okay. Yes?
Inside, so one line up from bottom, you have the sum over xi squared plus n0 over n plus n naught.
Exactly.
Why is it divided by n plus n naught there?
It should not be. That's correct.
Okay.
Yes. Thank you. Thank you. Thanks for noticing it. Yes. Because we already did this here.
Yeah.
Right. Thank you. Any other questions? Basically, the condition that I will get here is, of course, that, let's say this is mu, that mu1 squared, well, we can actually do it, has to be less equal than mu2. Right? That's the condition that I'm getting, because otherwise I can get negative variances, and of course that does not exist. Okay. Any questions so far about Gaussians? And trust me, this is the simplest way of deriving it. Every other way is many pages of essentially boring algebra. Okay, good. Yeah. Now let's get to something really convenient, namely called collapsing. And we effectively did that already anyway. Because it basically means that if we want to predict something, all we have to do is just, add this extra observation into our data set, right? So if you think about it, you observe some data x, capital X, and you want to predict at a new point, little x. Well, this is nothing else than, just using Bayes' rule, P of x, as it would have been generated by the data, right? Sorry, by the parameter theta, times the posterior probability of seeing theta given the previous data. Because what we ultimately want is, let's say I perform 3 measurements of the voltage in the sockets. I want to be able to predict how likely a 4th measurement would be, right? Now, the good thing is Okay, this is an integral. Okay, so let's actually expand it a little bit. Because this is just, by Bayes' rule, x parameterized by theta times p of capital X parameterized by theta times p of x fake parameterized by theta d theta. This is really just plugging in Bayes' rule and expanding terms from here to there. So, okay. However, since I had no particular assumption on, in which order all this data is actually observed, I'm assuming they're all IID, I can all throw them into one bin. Right? And now I have a slightly larger data set. Which is, okay, I have to solve the integral given theta d theta. Now, why would you care about this? Well, because those integrals have usually been already solved, and you can just look them up on Wikipedia or, basically Maple or, Mathematica will know about those integrals. Basically, somebody else did the work about 100 years ago, maybe more than 100 years. So let's be lazy. All we'll do is we'll just plug this integral in, and we can now work out exactly, what the data would look like. And then we can use this to read off directly p of x given the rest. So that's where this is really useful. So about 5 years ago, you could have written a paper in PNAS about this. And it's just this very, very simple line of math. But you can, of course, also make it really complicated and spend half a page on it. So as you've noticed, I've basically managed to derive all those things without ever specifically touching any exponential family distribution by just making reasonings over the overall functional form. So basically, this is about the laziest way how you can derive it. Yes?
These would work for, because here, where's the exponential family? But
so the exponential family is implicitly hiding in here, right? And what happens, however, is that now p of little x given capital X, this is not necessarily from the exponential family now. So what will actually happen is that, for instance, in the discrete distribution case where you have then a conjugate, Dirichlet multinomial, for instance, so this will actually look like the Laplace smoothed estimates. But for a Gaussian, for instance, you will actually get something that looks like a Gauss-Wishart distribution, and you'll have, funky log determinants and other things in there. So the algebra will look a little bit uglier, but that's essentially all handled underneath by your exponential family distribution. These are things that you will end up dealing a lot with if you have priors in graphical models. And yeah, usually when people talk about it in papers, it is not very clear how the mechanism works. So that's why I thought, let me go. So this is maybe a little bit advanced stuff, but it'll unscare you a lot in the future. Okay, so let's actually look at how this works in practice. So we have some data. We have maybe a couple of outcomes for rolling a dice. We have actual counts. We have a maximum likelihood and map estimate. And you can see that basically the map estimator smoothes things a lot more towards, 1/6. And what you can also see is that depending on whether I have only 6 observations or 100, the smoothing towards 1/6 is much, much larger. So compare those two numbers, for instance. So yeah, about 10 data points or priors per parameter. So let's see, the honest dice, and it's just totally way off. And the map estimate is a lot closer to what you would expect to see. Of course, now let's see what happens if I taint the dice. And for a tainted dice, so in this case, what happened is that 6 was much more likely and that the 1s and 2s were much less likely. The maximum likelihood estimate picks up on this faster. So I can be misled by my prior. This is exactly why you want to actually design your prior in a meaningful way. This is really just adding the counts that we did before. And yeah, there's probably not enough time right now to talk about other priors like L1, L2 smoothing, and so on, because this is, this will probably need a little bit more optimization. So we can cover that early next week. I just want to give you, well, actually, since it's only one slide, maybe we can just quickly talk about it. But first of all, there's a lot of stuff here, lots of links. You can follow them through. This will give you way more detail than what you probably want to know about this. The parameter smoothing. So designing conjugate priors is one possibility of doing this. Another way is simply to say, well, look, my parameters should just be small in some form. And you've probably heard about weight decay or just imposing a normal prior on my parameters. This is basically what's happening here. And a sparsity prior would be this guy here. And so I will get a posterior, which is basically, just my exponential family's likelihood. This term here. And I will get a contribution from my prior, which might be this term here. Right? And then all I have to do is solve an optimization problem. So again, I take a derivative. And the unfortunate thing is that now in many cases I cannot solve it in closed form anymore. However, this is what people do a lot when they, for instance, talk about penalized maximum likelihood methods. So you may have, for instance, implemented logistic regression with an L1 or an L2 penalty or downloaded liblinear and done something like this. That's basically what these algorithms do. They solve this optimization problem. And now it doesn't have any closed form solution anymore. With conjugate priors, chances are much higher that you can work out the closed form. Here, well, you just have to optimize. Okay. Any questions? Okay. So recitation is again tomorrow. Homework 3 and 4 should be out. Homework 5 and 6 are to follow soon thereafter. And you can advance submit homework if you want, of course. And yes, the leaderboard. So I need to keep my promise. So there are, for Pablo, there are two. Is Pablo here? Okay. So could the first 5 teams please come here? Yeah. So nicknamed perfect totient, drop table students, and a ladder. And so Pablo gets 2 chocolates. Everybody else gets 1. So let's give a round of applause again to. Okay. So thanks, and for the next homework there shall be chocolates again. So basically do well on the leaderboard and you get some chocolates. Thanks. Dear cameraman, if you could please